Preparing to stream. Actually, the technology has worked pretty good today. I'm very surprised.
Well, the whole world relies on it now, so it better work well.
And actually, it's
Absolutely.
surprising how many people are wanting in these rooms.
Hey, you know what?
Keep upgrading.
Ed was surprised. So, all right. I think we're good. So, what do we have?
I'm not host yet. I can't share yet.
Sorry about that. Yeah. And make host. And there you go. What?
Okay. Let's
Now
see.
we have Dr. Porter.
Yeah, there you go. How do I get my chat back? There we go, chat.
All right.
Still got a, oh, looks like it just turned to 4:30 here.
Yes, you're right on the half hour, so you are good to go.
All right. Hi there.
So,
oh,
what
I guess you can introduce me, don't you?
I can. So this is Mr. Bill Porter. Again, most of you should know him, probably know him. He is going to be doing a presentation on, at least last that I saw, power distribution and power injection. So I am going to turn it over to Bill. Welcome.
Oh, thank you, Carl. Well, I was told I had to, are we recording? Yes, we're recording. I was told I had to use the template. So there you go. There's the first slide in the template. And then that meets the requirement, so I can get rid of that. This is actually my presentation. I don't like PowerPoint. This is a little different. This is actually my display from a couple years ago. I have given this presentation before at the expos. So there's not much new if you've seen it before. Even shorter PowerPoint than Ron. I'll take that award. So we're going to be working our way through my display as we talk about the subject. And again, the subject is power injection. So who am I? I'm an electrical engineer for the US Navy. I specialize in robotics and embedded systems. I've even had Pitts called me a couple times when he was working on controllers and things like that. My history in lights, I didn't buy my first house to 2014. My first light show was in 2015. My first 2 years I did Vixen, and then I jumped over to X-Lights. That's not to say I wasn't lurking for much earlier than that, because the truth is I was lurking for much earlier than that. Oh, I broke Prezi. Let me just use these. Before that, I actually did lights when I didn't have a house, when I lived in an apartment. That's actually a picture of our wedding. My wedding attire, my wife's wedding attire, actually had Vixen 2 sequences embedded into it. We had a 3D printer. We did some fancy stuff with 3D printed table centerpieces, and our wedding invitations even had an embedded sequence in them. So what I'm trying to say is I do LED. I do crazy stuff with LEDs. I have a tie there that you've probably seen at the expo that plays Tetris. I got some crazy glasses. That was a funny picture because I was at a science convention in DC, and the photo op astronaut asked for my picture, which I thought was pretty cool. So I was just walking by him and he grabbed me and he wanted a picture. So anyway, why am I here? I'm here because of power injection. And the reason I get this presentation a lot is because I like to argue that it's not hard. So let's jump right into it. So we're going to fly over here to my garage. So some background. So here's what I want everyone to do first. Can you get really close to your monitors for me? Just get really close. All right, just look at that. Perfect. Because the first thing I want you to do is forget everything. And the reason of that is because power injection is not hard. It's just people make it hard. I'm gonna draw my camera just like it's out of the way. People make it hard. So if you search power injection in the Facebook group, you get all sorts of fun results. Whoops, I'm flying around too fast. And the reason is there's many ways to skin this cat. There's a lot of right ways, there's a lot of wrong ways, and confusion comes from trying to, when a newbie comes in and asks for advice in power injections, they get all these different competing rules or ways to do it. That's where it gets confusing. So I'm not going to say this is the right way. I'm not going to say other ways are the wrong ways. What I'm teaching here is just my way. And my way is I try to make sure that you guys are successful. because really I don't want 1,000 people PMing me after my presentation saying we followed a rule and now our lights are flickering. Why is that? So what I'm teaching is a way that you won't have issues, because I don't know about you guys, but once I build something, I want it to work and I want to go back and figure out why it's not working. And it's because of science. The reason I don't really want to teach you the science of power injection because it's very complicated. There's things like wire gauge, wire length, wire composition, wire impedance, connector impedance, all sorts of fun stuff that really affects whether or not your pixels will have issues. So I'm not going to go into that. And this is kind of my favorite quote. And just another, hopefully, reason why you should listen to me. I love this quote. Anyone can build a bridge that stands, but it takes an engineer to build a bridge that barely stands. That's the motto of my life right now. Another thing before I go too far past this, I will say this community, this hobby has exploded. And if you're here for power injection, I want to clarify that power injection, you get your hands a little dirty. You're going to be, what we're talking here is we're going to be talking about cutting and soldering wires or connecting wires together. If you're a guy that really just doesn't want to deal with that, if you just want to plug some lights in and have it work, you kind of don't want to get into power injection. You just want to kind of go the route of only putting 200 pixels per port and being done. That's a valid way to create a light show. But if you're not comfortable doing wiring or hooking wires together, I don't think power injection is really for you. But anyway, you can still tag along and learn some things. So before we get too far into how to do in power injection, I want to clarify some terminology. What is power injection? So here's my definition of power injection. Power injection is any time power enters a line of pixels separate from the source of data. This can be done at multiple points or from one point. So for example, that top example, and I tried to do, please don't beat me up for my terrible paint drawings, but I'm trying to do some basic wiring diagrams that people can follow to kind of understand the premise of what I'm talking about. If you just hook a string of pixels up to a controller, there's no power injection there. If you look at that second example where the positive wire enters the pixels from the middle of the string, which I've actually seen some people build props that way, I consider that power injection because you're injecting the power at a different point of the data. If power follows the data, it's not power injection. If power goes separate from the data, it's power injection. What is a power injection run? I'm going to call the length of wire between your controller box, which is your orange square in this diagram, and your pixels. That's going to be the run. That's just going to be some separate cable that carries more power to your pixels. That point, it attaches to your pixels, we're going to call power injection points. So to make sure we're clear in definitions, that's a power injection run. This is the length of wire from your controller boxes to the separate point of power where you're powering your pixels, and where it connects to those pixels is called the power injection point. So moving on. Why do we do this? Well, the reason we do this is because voltage drops. If you plot pixels down the wire and you plot each point where the voltage measure that point, you'll notice this actually forms a curve like this. Or to put it in a little more easier to understand picture, if you took a voltmeter and measured the beginning of the string and took a voltmeter and measured the end of the string, you'll find the voltmeter at the end of the string reads a lower voltage than the voltmeter at the beginning of the string. This is true for anyone who wants to fact check me. This is only true when your pixels are actually outputting light. If all your pixels are off, you won't see much of a voltage drop. Voltage drop only happens when you have current, meaning the lights are on and drawing load across your pixels. By adding an additional wire, we distribute the current and reduce the current on any one set of wires. Less current equals less voltage drops. That's what we're doing with power injection. We're allowing the current to travel back to our control box along multiple paths, not just the one path of our pixel connection. Okay, quick note on voltage selection, because I've already seen someone trying to razz me for that. This is a common question that usually is what kicks off the power injection discussion. Why do we have 12 volt and 5 volt pixels? Well, it's because there's a trade-off. Neither is perfect. 12 volt allows for more voltage drop before affecting color and brightness. However, 12 volt pixels draw twice as much power as 5 volt pixels at the same brightness. Electricity is cheap. I'm not trying to beat up people for that. But when you start talking about how many power supplies and enclosures you need to put into your display, now you start to get into some trouble. So for example, a 350 watt 12 volt supply at 30% brightness gives you 1,500 pixels worth of power. A 350 watt 5 volt supply at 30% brightness gives you 3,200 pixels of power. This is why 5 volt still exists, even though 12 volt is nicer for building props, because you can put more props on the same power supply at 5 volts. 5 volt pixels are also cheaper, and I will also, at least in my experience, because my show is actually both, I'm 50/50 5 volt, 12 volt. I always have noticed that 5 volt pixels are also more reliable. I buy mine from the same source, and I found that the 12 volts, I just have more pixels I have to cut out, and I barely ever cut out 5 volt pixels. I believe that's just because they're less parts. They have less parts inside so that they have less to fail, and they're more reliable. But that's just my experience. I don't have data across the industry to prove that. What's my suggestion? Like I said, I do both. I have every single one of my controller boxes is mixed voltage. When I wire up the controllers or the power injection runs, I select either 5 volt or 12 volt based on what prop it's going to be plugged into. 12 volt for outlines, trims, long distance models makes more sense. 5 volt for grids and some configurations of pixel trees and other dense models makes more sense. Basically, my advice is design the model first, see if it can be wired reasonably either for 5 volt, and if not, drop to 12 volt. This is an example of one of my simpler control boxes. I just have an F4. Most of my show is with smaller controllers since I do power injection. So I just have an F4 and a power distribution block, which we'll talk about in a minute. And then I have the 2 power supplies, a 5 volt and a 12 volt. And then I label the power injection connectors, which we'll talk to you about later, based on the props they're plugged into, whether they're a 12 volt prop or a 5 volt prop. And then I do different color labels to make sure I don't mix up voltages. So basically, to settle this argument, I'm not going to try to tell you one way is right or wrong. Just do whatever you want. If you want to have a whole bunch of power supplies just to make wiring easier, then go do 12 volts all across the board. Or if you want to save a little bit of money and do lots of soldering, you can do 5 volts across the board. Both will make you a nice show, and you'll get some nice fans, and then that'll be the end of it. One more note, 12 volts. There's 2 types of 12 volt pixels. And I think Keith Wesley's actually he's done some extensive testing and actually proven a lot of my theories because I helped him do some of that testing. And he'll be talking about that tomorrow in his presentation. But basically, regulated 12 volt pixels, I only buy regulated. They are more consistent on color and brightness down the line, and they can actually get you a little bit further down the line than resistor 12 volts. So I pay the couple bucks more, whatever it is, for regulated pixels when I buy them. I don't buy resistors. The other thing that's not so common anymore, but a couple years ago it was very common, there was this, a lot of people started having what we call the pink effect, where when a pixel was supposed to be off, it was turning pink. That was due to a design flaw in resistor pixels. Regulated pixels would never have that problem. Okay. So now we're going to start getting in the nitty-gritty. Execution. How is it physically done? Power injection is connecting wires together. So how do we connect wires together? Well, there's a couple different ways, and it's all about what you're comfortable with. Some old school engineers, electricians will still fall back on the solder it together and do the heat shrink, which is valid. You can just do a soldering iron and a heat gun to shrink your tubes there. I love these things, these solder shrink tubes. My entire show has been 3 years exclusively these solder tubes. I've used thousands of them. They're super reliable. They're super easy. You basically trim your wire, you shove it in the tube, and then you heat the tube up, and it's both solders and shrinks at the same time. So you've created a good watertight connection with one go. And that removes the soldering iron. You only need your heat gun. I will say, people, there is a minority that hate these, and every time I try to find one of those people, I try to talk them through what they're doing that could make it a problem. The first is they're old school and they try to twist the strands of the wire together tightly before entering into the tube. You don't do that. You leave them loose and frayed like the wire on the right. That way the wires, the little strands of each wire can intermingle. The next thing they do is they're really timid with the heat gun because they're used to too much heat gun, meaning makes the tube burn up. These tubes are different material than normal shrink tubes. With a normal electric heat gun like that, you'd be hard pressed to get it hot enough to actually melt the tube. So I say you got to throw out your old way of thinking with shrink tubes and being timid. You really got to get the heat right on the metal to melt that solder. I also don't recommend butane torches with these because butane torches with these will burn them. And I think a lot of people struggle when trying to use butane torches with these. But I love these. If you want to go crazy like me with power injection, I recommend these. You'll see them in some of my examples coming up. This is my preferred way. Some people still love crimping. So this is another way people do it. They crimp it and then shrink the crimp to create a seal. That's another valid way to do it. And then you can always try the plug and play method, which is a lot of your vendors will support selling you power injection tees, which are plug-in T adapters that allow you to inject power without doing any soldering, and that makes the tool just your hand. So if you really want to try power injection, but you're not willing to cut cables, there's always this way. Though my only argument against this is you sort of lose the cost savings advantage of power injection if you go these ways, because the cost of those T's adds up. Okay, now, we're not quite there yet. We need to talk about one more thing if we're going to start going crazy with power injection, and that's, of course, protection. Because yes, we should always use protection. By that we mean, of course, fuses. You've noticed you have fuses on your control boards. If we start running wire from our power supplies directly to our pixels, we should really have fuses in line with those as well. So some comments on fuses. Fuses protect wire leaving the enclosure. The power supplies have built-in protection of different varieties based on which power supply you get, and that protection will protect the wires between the power supply and the fuse block. But you still need to have either a distribution board or a fuse block to protect the wires leaving the control board. And you can have one fuse protect multiple power injection runs. So hang with me. Let me get through all these explanations, and I think you'll be able to understand what I'm saying here. So basically, here's my bad paint drawings again. So for example, one fuse can protect this entire line of pixels, even though we have power injection runs after the fuse. How do we select the fuse? Well, I hear a lot of people ask the question, how many pixels can I run off my 5-amp fuse on my controller? And that's the wrong question to ask, because the load and the fuse really don't go hand in hand. Fuse size is determined by the smallest gauge wire after the fuse. So you have to think about what fuses you're allowed to use depending on what wire you're allowed to use behind that fuse. The reason for this thought, the reason we think this way is because we don't want the wire to become the fuse and burn up. Here's just a rule, or here's my rule. And again, I think the first question people are going to ask is, yes, people have done testing. An 18 gauge relay is an 18 gauge, it's slightly more. I agree with that. This is still my sort of not as conservative rules for fuses with pixel wire. If you're doing 22 gauge pixels, you got to do 3 to 5 amps. You can't go any higher. If you're doing 20 gauge pixels, you can go a little higher, 7 amps, maybe 10. And if you do 18 gauge pixels, 10 to 15. I got it that 18 gauge pixels might not be 18 gauge, but even if you consider it that way, the conservative value of these numbers based on the slightly thinner wire sort of cancels out. So I still live by these rules when I'm doing fuse sizes based on pixels. To answer a question that just popped up, where you buy your pixels depends on what size wire it is, and some vendors tell you what it is and some vendors don't. So check with you where you're ordering them if they can tell you what gauge wire they're using for the pixels. The companies I usually buy from, like Wired Watts or Crockett, they usually say up front, this is this gauge pixel you're buying, and sometimes they offer you to save a little couple pennies to buy smaller gauge wire. I always try to make sure I'm buying 18 gauge pixels when I'm buying it. Once you have set your fuse based on your wire size, now you can play with brightness to enable more pixels to be run behind that fuse. A couple people hate me for saying this, but this is still again, we're learning my system. In my system, you can do this. So basically, if you have a 15 amp fuse and you want to run more pixels, you bring your brightness down and then you can run more pixels behind that 15 amp fuse. So this is the only equation I'm ever going to ask you guys to remember from this presentation. Fuse size divided by pixel current times brightness equals the number of pixels you're allowed to have. So a 15 amp fuse times the pixel, or divided by the pixel current, which is always 0.055, times the brightness. So for example, if I'm going to run my pixels at 50% brightness behind a 15 amp fuse, that means I can run 545 pixels. The next equation example, 30% brightness behind a 5 amp fuse means I can run 300 pixels. So only equation I'm going to ask you to remember for the test later. And that's just the equation to figure out how many pixels you can run behind your fuse. Note on distribution boards. Here's a Crockett distribution board. Don't change the fuses in these behind their original value, because you don't know what other limits on that board exist to justify that 5 amp fuse. Because remember, there's traces on that board that count as wire connecting to those connectors. And if those wires weren't made thick enough, you still have to have a fuse that's rated for the smallest wire behind the fuse. This is a Crockett Fantasy of Lights distribution board. I think Dave Pitts sells them. Wired Watts sells them. You can buy distribution boards from a lot of your favorite vendors. Yes, the equation is the same for 12 volt and 5 volt pixels. Notice voltage isn't in this equation at all. That's because both 12 volt and 5 volt pixels have the same pixel current. So if anyone's interested in why we say 12 volt pixels draw more power, it's because it's the same current at 12 volts. So no, it does not matter. This equation does count for both 5 volt and 12 volt pixels. If you want to go bigger, and this is actually what I use in my show, I use these marine fuse blocks because they're rated for 30 or 40 amps, I believe, and I typically would put 15 amp fuses in there. So if you did want to go a little bit higher than these 5 amp boards, I think either Crockett or Wired Watts does have a higher current board as well. I think they offered that before I started building my boxes. So my boxes are built with these marine adapters. Okay, we got safety out of the way. Let's see if I've got any safety questions before I go on. I think I got them all. All right, so now let's actually talk about the rules to my power injection system. And there will be a test later. We'll call these the rules to live by. First rule, always inject both positive and negative, or V plus or ground, at every point. So that first example I had of power injection is not a good example because the negative wire and the positive wire are connected to the pixels at different points. I know some people have built props that way. I'm telling you don't. And the reason for that, Keith may actually go to in your pixel flicker, but basically you always want to make sure that the pixels are seeing the same sort of stuff between their data lines, their ground line, and the positive line. So they must always be connected at the same points. That's the first rule. Second rule, always inject at the beginning. So, okay, now that running example of power injection is now incorrect. You must always start injecting at the first point of your pixels. So we can still have our injection point further down the line, but we must always start at the beginning of the pixel string. That's the second rule. Count, my favorite. So this is the thing that you hear 1,000 different answers to. Tonight, my system, it's 50 and 100. No more than 50, if you're 5 volt, no more than 50 pixels to any point of power. If you're 12 volt, no more than 100 pixels to any point of power. But that goes both ways. So the reason I'm saying it this way is just to make everyone clear in what we talk about when we talk about how power goes both ways. What we're saying is if it's 5 volts and the rule is 50, you just need to pick a point on your string and be able to count to some point of power 50 either way. So what we're really doing in this example is we're really attaching our next power injection point at pixel 101, because we could pick any pixel between 1 and 100 and be able to count 50 pixels to a point of power. So if you want to, this is the rule, but if you want to think about where you actually need to tap your wires, then the rule really becomes you tap your wires at pixel 100 for 5 volt, or you tap your wires at pixel 200 for 12 volt. That way it's either 50 or 100 pixels to the nearest point of power. Is everyone clear on that? Nearest point of power quotes. Is that my new quote now? Should I get a shirt made? I will say if you do use the pre-made power injection tees, in the early days, some of those power injection tees didn't send power both ways. They'd send it just up and not down. I don't think that's the case anymore, but if you do buy them, just to check to make sure that's not the case, because then you lose the benefit of sending power both ways if it actually doesn't send power both ways. If you do multiple power supplies, because we'll get involved in this, you can actually do long runs of pixels where you have to split up power supplies, and one power supply will power one section of pixels, and another power supply can do another section of pixels. It's a good idea to cut that positive wire between your two sections. You don't want to create a problem where one power supply is trying to take on the entire string or actually feed back into the other power supply. So you always want to make sure you create that point of isolation so that doesn't happen. Excuse me. I want to bring up this picture again real quick. So when I shove this slide, people then go, well, does that new pixel underneath the red arrow count as the new beginning of a new string? And does that not violate your power injection at the beginning of the string? So let's clarify that real quick. What we're saying is you always need to start powering at the beginning of the string with respect to ground. So because the ground was not broken here, because you should not break the ground here, it should continue through. The beginning of that string is still the first pixel all the way on the left near the first power supply. It is not there, that where the arrow is not a new string with a new first pixel that then violates this rule. So we're modifying this rule to say always start at the beginning of the string with respect to ground or the negative wire. You should use fusing to isolate multiple sections of your string if you are going to do this. And then again, you also have to cut the positive wire for your different fuse sections. So if you're doing a big grid where you have multiple power injection runs, each with their own fuse, you do need to cut that positive wire in your grid to make sure you don't have one fuse that tries to take on all the load of all the pixels. Use good power injection cable. I love this stuff. So I love these connectors and I love this cable. I love the cable because I live in Florida and that is UV stable cable. I've had it out for years and the sun doesn't bake it or dry it out or crack it. Most of my show is wired with 14 gauge power injection cable. And then I use that because I can do lots of runs off one cable, lots of power injection points off one cable, excuse me. So I buy that on Amazon and it's actually pretty cheap for the fact that it's pure copper cable. The price may have gone up, but the last couple of times I bought it, I was actually really happy with the price. And then I love these MUI connectors. These MUI connectors are knockoff automotive power connectors. Someone just pinged me on Facebook a month back because they bought the wrong ones. You have to make sure you buy the ones that have those red inserts because those are the only ones rated for 14 gauge. So you get 10 connectors for $10 off Amazon for those MUI connectors. Just make sure it's the picture with the red ones in it, not the yellow ones. So this is what I use for my actual power injection runs. And I'll show you some examples of this in a minute. And you'll see how I connect my props. And maybe a couple of questions may click once you see that. Limits on power injection runs. You need to limit the total number of pixels at the end of a power injection run based on the size wire used for that run. And this is, again, why I use 14 gauge. Because 14 gauge will give me 350 pixels of power at the end of that power injection run. If I use smaller power injection cable, like 16 or 18 gauge, I get less pixels at the end of that cable. One complaint that I see in arguments on Facebook about power injection is it makes your display messy with cables, and that's not true. It only makes your display messy with cables if you use small cables. Because I use larger cables, I have a lot less cable in my display, as one cable will daisy chain down a bunch of props to make them all powered. Here I'm using a grid as an example. If we have a 500 pixel grid that we want to power inject with, you need 2 power injection runs. You want to split that up into 2 250 pixel zones of power. And that way you only have 2 14 gauges coming from that grid back to your control box. And that way you've got nice clean power to your pixel grid there. So just as a thought, think about how many pixels are at the end of your power injection run, and you need to make sure you stay under this number. Okay. All right. So I've mentioned this a couple times, and I think people have said they like my power injection method because you build it into the model, you don't really build it into your control box. And what I mean by that is I keep it simple. All my props have 2 connectors on them. The normal 3-pin twist lock connectors that we're all familiar with, plus one of those 2-pin power injection props. And I'll show you pictures of that in a minute. Another thing, I've said these are all rules. They're rules, they're guidelines. What I mean by that is you can fudge a little. Those rules were built in that allow you to fudge a little bit and you still won't have problems. So what I mean by that is if you need to go 55 pixels and 5 volts, go 55 pixels, it'll probably work. Just don't go far off that number. But think about that when we go through these examples, that some of these examples may have been fudged a little bit, but it's okay to fudge, just don't fudge really far. So here's an example, these 100 pixel Holly things. I love this one because this one demonstrates a method of power injection that defeats the arguments against power injection because it's very simple to be able to wire these. And what I mean by that is this Holly is 100 nodes. But what you notice when you look at the wiring view from X-Lights is that node 1 and node 100, the last node, are right next to each other. So in this case, what power injection means is literally just tie the beginning and the end together. And that allows you to use 5 volts for these Hollies. Because if you think about it, if you tie the beginning and the end together, now we satisfy the 50 pixel rule on a 100 pixel prop. Because now we can pick any pixel along that string and say it's within no more than 50 pixels to the point of power. So I literally just, and let's see if I can scroll in, tied the beginning and end of the pixels together when I made my wiring harness for that prop. So that prop can run 5 volts, full power, full brightness if I wanted to, with no additional power injection cable, just by tying the beginning and the end together and using those solder shrink tubes to connect the actual electrical connection. Now, these props are really far away from my control box, so I still added a power injection point there. So you see that red and black wire heading up to one of those automotive connectors. That's my standard connector for power injection, just because that prop is about 50 feet away from my control box. So that much cable length, I did have to add a power injection point just to keep the voltage high by the time it got to the prop. But otherwise, if this is right next to a control box, you can just get away with a standard 3-pin connector with 5-volt pixels just by tying the beginning and the end together. That's how simple power injection can be. It can literally just be tying the beginning and end together, and now your prop works better. All right, let's do another example. So my display has these little mini trees along my front line. These mini trees are 70 pixels each. There's 50 in the tree and 20 in the star. When I bought all my pixels, they came without connectors, since obviously you notice I like soldering my own connectors on. So most of my pixels come with flying leads anyway. So I already had to solder 50 and 20 together just to come up with the 70 pixels for my tree. I only have a 4-port controller in the front of my yard, so I want all 4 trees to run off one port. That way I don't have to get a bigger controller out there. And just based on preference, I've noticed that I like to run those trees at 40% brightness. So with those numbers, what I decided to do is just add a power injection point between the 50 and 20 pixel string in the middle of the tree. So where the pixel 50 goes to pixel 51, right at that connection of the star, I added a little connector there to inject power. This was early in my days of building my display. I actually used these trailer connectors before I switched up to the automotive connectors. So that picture is the trailer connector I used to connect my power injection run to my tree. So that was an example of how I built my prop, and this is a good example of how I built my prop with power injection. So I built this prop with power injection, and all that meant was I added an additional connector right in the middle between pixel 50 and 51 when I already had to solder those two together anyway to add the 20 pixels to the 50 pixels of the tree. So now the way it's wired for my control box means I have one 3-pin normal pixel connector, that's the green lines. Comes out of my control box, goes to the first tree. The first tree has an output, which then goes to the input of the second tree, and so on, so that all 4 of my trees are in one chain of pixels. So one pixel port is running all 4 of my trees. Separate of that, I ran power injection wire, which is the red wire, to those little connectors at the neck of each of those trees. Now this satisfies all of our rules. I'm injecting at pixel 1, I'm injecting at pixel 50, pixel 120, pixel 190, and pixel 260. So that's no more than 70 between points of power, or 35 from the nearest point of power. So it's actually more conservative that way, but it was just easier to build those props since I already had a solder there anyway to put those points there. So we satisfy our rules. Let's talk about pixels and current. Now altogether, those 4 trees make 280 pixels. At 40% brightness, that's a 7 amp power draw. I used a 10 amp fuse, and I used 16 gauge wire there. I used 16 gauge wire there just to make it smaller wire. So that, in that particular case, I used 16 gauge wire just because I could, because I wasn't actually doing a lot of power injection draw there. So we've satisfied all our rules. Now let's compare this exercise to if we had used 12 volts. Because then you can kind of start to see that sometimes, it's almost the same anyway. So 12 volts here saves you from 2 of the injection runs. I could have skipped the first tree and I could have skipped the third tree actually running power injection wire. So yeah, it would have saved me 15 feet of wire, but it also would have put a lot more load on my power supply. Just those trees would have used 26% of a 12 volt supply at 12 volts, but at 5 volts, they're only using 11% of a 5 volt supply. And I only have one power, I do have 12 volts up there too, but I have one 350 watt 5 volt supply already up there. That's running my mini trees and my pixel poles and the new stuff I'm adding this year, and still has room to spare. Whereas if I'd done all that with 12 volts, I would have hit the limit of 12 volts already. So I do, in this particular case, I do add 50 feet more of wire to my display, but I also allow myself to keep adding props without having to increase the size of my control box. So this is why I try to always wire for 5 volt, but then if it becomes too difficult, then I wire for 12 volts. That's what I do when I'm designing my show. All right, so we ready to take the test? Who wants to volunteer? Oh, I'm just kidding, I won't put anyone on the spot. So let's do a couple more examples. I love this example. I have, I think Ricky, no, who is it?
Carl will take your test.
Carl will take the test. Oh, there you go. Oh, I know, it's Crockett. So Crockett has this spider web as well.
I'm sorry, I wasn't hearing. There was some static in my ear.
We're going through a tunnel. Don't worry about it. So this spider web I love is another good example of how some thinking can let you build a prop that actually is easier to put in your show based on how you build it. So I ended up using 5 volts. So did Daryl at Crockett Fantasy of Lights. The way Daryl did it is the way people hate power injection, because he ran like 4 or 5 extra wires or cables to this web to do power injection. I was like, Daryl, it was crazy. It's all that wire, you don't need it. So let's apply my method to this and see how we can wire it. So if we just look at the wiring diagram, so we've exported the wiring diagram from Xlights, and how it's wired is a big spiral. So if we just go by the rules of the road, let's pick, and let's start with 5 volts. Like I said, I always start with 5 volts. Where would I have to power inject? I'd have to power inject to pixel 100. Well, excuse me, I have to power inject to pixel 1, then pixel 100, then pixel 200, then pixel 300. Okay, that's feasible, but that's a lot of wire running around the prop. So why don't I fudge my rules a bit and try to get all those pixels to be in one line? So if I fudge a bit, now I can inject the pixel 1, pixel 108, pixel 168, pixel 240, and the last pixel 324. So I added 1 extra point of power, but now I've lined all my power injection points into one line. And you're probably thinking, oh, I see where he's going. So now I can do cleaner wire by just injecting one wire through that one little, what do we call that? Leg of the spiral, or yeah, I'm not sure. Spokes, excuse me, spokes. That one spoke is all the power injection wire I have in my prop. So I have, just like the rest of my props, I have a data connector in, a data connector out, a power injection connector in. So that power injection connector, that's my 14 gauge wire that's carrying most of the current for this prop, is simply an extra 2 feet of wire that's spliced multiple times down that prop. And I did it in a really clever way, because I just took an X-Acto knife. I took an X-Acto knife and I didn't cut the wire. I just used an X-Acto knife to pull off the insulation at certain points. And then I slid those solder shrink tubes all the way down the wire. And then I would cut the pixel wire, strip it, and just stick it in both sides. So my power injection wire, my power run wire is not actually cut here. It's just stripped. And then my pixel wire is cut, shoved in, and I hit it with a heat gun, and I'm done. Very simple. I did this in like 15 minutes. Excuse me for a second. I had to take a cough. Thank you. Oh, I think I just broke Prezi. Come on. Okay, there we go. So let's move on to fusing now. If you've had one of these webs before, you've probably found 30% brightness is pretty good. You sort of get the grid effect with these because they're so dense. You want to use a lower brightness to deal with that. 30% brightness of 340 pixels based on the equation I taught you. If you run the math, it's a 10 amp fuse. I have a single 14 gauge power cable. It's about 20 feet. And I ended up running this entire prop at 5 volts. So this entire web, I did it 5 volts. Excuse me. Again, let's see our voltage check. What would we have done at 12 volts? At 12 volts, we could have eliminated some of those splices, but notice we'd still have the same length of wire required to actually build this prop anyway, just less splices. So by using 5 volts, it didn't actually cost us more wire. It just cost us a few more minutes of soldering and some more solder shrink tubes. But again, what's the difference of load on my power supply? At 12 volts, this would have taken up 26% or a quarter of a 12 volt supply, but only really takes up 11% or a tenth of a 5 volt supply. So again, I like to make sure my control boxes are available to add props as I see fit without adding more control boxes. And by keeping my loads low and using 5 volts, I can keep adding more props to my show without having to add more control boxes. This is another example of how I do my power injection, where I talked about how I use a razor blade to cut the insulation of the wire, but not cut the wire itself, and then slide those shrink tubes down the wire, and then just shove my pixel wire into them and heat the whole connection. So these are old pixel grids I don't use anymore. And and I did the same thing here just to make the power injection a little easier. It was very easy to do. Again, 10, 20 minutes with a knife, some strippers, and those shrink tubes, and it's actually pretty easy to be able to cut wire and attach wire to your props. And that's a pulled out view of the picture. Again, all my props are built this way. Data pixel wire in, power injection power in, and data pixel wire out, because I cascade a lot of my props together to minimize how many controllers I need in my show. I think I was at 6,000 or 7,000 pixels 2 years ago, and I only used 2 F4s. And I still had 6 ports open on 2 F4s for my entire show. So I'm what Dave Pitts likes to call a port packer, because I use close to the max 640 pixels per port on his controllers. So again, let's review. Both wires at every point always start at pixel 1. No more than 50 pixels for 5 volts, 100 for 12 volts. But that counts for either way. Isolate power supplies, isolate fuse zones, use good wire for power injection, and max pixel count per run. Give me one moment, guys. I'm going to grab some water. I'll be right back. Sorry about that. I ran out of water. It was starting to get hard to talk. All right. Any questions? So this is actually the end of my presentation. Now I can start taking some questions, and I think I did okay in time. We got time. All right.
Yeah, you're good. You got a bunch in the chat.
All right. Let me start at the top and work my way down. Oh, actually, it's from the other show.
Yep. 540. Starting with Gil, how far can you go on a straight line using 12 volt versus 5 volt?
There's not a solid answer to that. Again, this, physics is hard. There's lots to it. The quality of your connectors, the quality of your wire, the composition of your wire all affect that answer. Which is why what I taught is a conservative approach that makes sure no matter what wire you buy or what pixels you buy, my method should work. So you can push it harder, but when you push it harder, consider that you need to test it to see if you pushed it too hard, because I can't tell you how hard is too hard without knowing exactly what you used.
Are you in the chat, or do you just want me to walk through them, Bill?
I'm going with the chat.
Okay.
This is true for unregulated 12 volt. New regulated 12 volt is 10% more power than 5 volt. No, it's all the same power, because it's not the regulation that affects that. LEDs are all the same LEDs, and they all require the same current to make the same brightness. So my rule about 12 volt versus 5 volt and how much more power it uses is true. What they're doing is they're selling 12 volt pixels that in the chip are less bright than 5 volt pixels. And that's how they can say it's only 10% more power, but it's half the brightness. So like I was very careful on what I said. 12 volt pixels use more than twice the power for the same brightness. And that's because it's the physics of the LEDs themselves. It has nothing to do with the method of regulation. What some of those strings are doing to be less power is they're just in the chip limiting the brightness to the LED to justify that less power. Yeah, pros and cons of both. I got it. He's only had 1 pixel fail ever, 5 volt. Okay, I told you that was my experience was. if there's a way to check if your 12 volts are regulated or not. I'll have to find the picture. I posted a picture to the Facebook group a couple times many years ago. If you can look closely at the circuit board, 12 volt regulated pixels have two big black chips on them. One's the actual pixel controller, the other one's the actual linear regulator. Resistor 12 volt pixels will have one black chip and a lot of extra little silver parts, because the extra little silver parts, they could be extra little black parts, but there's a lot more of them are the resistors. So if you get two big black blobs, you have regulated. If you've got one big black blob and a lot of little silver parts or little black parts, then you have resistor. Yeah, we talked about wire gauge. I think I got that one. It's here. The Dave Pitts board, distro board is nice. I agree. Yeah, there's the equation for power. Yep. Yeah, DIY LED used to be my vendor of choice. I'm not sure where they are right now. I haven't looked at them in a while. Connect injection in a line. Saw that in Canister Christmas. I hope I reinforced that, depending on what you meant by that. Someone else is a port packer. Port packing is awesome. Till a pixel at the beginning dies. I agree, port packing is awesome until a pixel at the beginning dies, which is why I hate 12 volt pixels, because that's the most pixels I've had die that I had to go out and cut out. Most of my 12 volt pixels that died, though, were C9 types. I've only had a handful of the 12 millimeter node types die, but I've had so many freaking 12 volt C9 pixels die. It's unbelievable. I hate them. I keep my C9 lines in their own port just because I don't want them to take out the rest of my props for how many often they were failing. I always do like extension cords at home. First pixel is male. Okay. About load on the house circuit breaker. If you've built a pixel display that's actually causing you a load issue on your house circuit breaker, holy crap. Because you can put a heck of a lot of pixels on a house circuit breaker since LEDs are so low power. I'm either 6,000 or 8,000 pixels, I forget. And my entire show is one plug. So I don't have any issues with that. You really have to be across the 10,000 pixel mark before you start thinking about multiple connections to your home or tripping breakers and things like that. Your wire is 3 connector. What I connected to that? Well, so my 3-wire pixel connector wire is the same as the usual pixel cable. Actually, I can start showing stuff in your hands now. So let me do this. Let me turn on my camera and see my messy hair again. So this is my normal pixel cable. So this is what you guys are familiar with, that little 3-pin right there. Each one of my props has the input and output to connect to this, just like your normal pixel props do. But then I also splice in my pixel injection wire. This is an example of my power injection run cable, 14 gauge landscape cable with male and female automotive connectors. So my props will have one of these connectors in to take in extra power and one of these connectors in to actually take in the power and data. So that's what I meant by those 3-pin pixel cables. It's the one you're familiar with. How do you know when to power inject the same power supply or add another power supply? Good question. I don't think I covered that well. That equation for power, you should apply, when we kept calculating power, let me bring that back. Let me share my screen again. Am I not host anymore? How am I not host again, Carl?
And I had to pull host back.
Oh.
Hang on. There you go. There you go.
Okay, thanks. Share. So if we go to our checks, I put the equation there. I didn't. Okay, so that one equation I taught you to use. Where's the rules? Oh, it was under fusing, wasn't it? Yeah. No, yeah, I won't be in there. So this equation that gives you, where we talk about amps, you basically use that equation to figure out how many amps all your strings will be on that power supply, and then you'll look at your power supply. Your power supply has different amp ratings. a 350 watt 5 volt power supply will say 60 amp, and a 350 watt 12 volt supply I think says 21 amps or something like that. So you want to make sure that when you do this equation and to figure out how much current you're going to draw on your power supply, that it stays below those numbers. Let's see what the other questions were. Okay, I gotta scroll back up. Sorry. Is it that? That's what she said. Apparently, I missed that one. One query I have is a 5 amp fuse in the board and a fuse in the power injections line. Same power supply. Is that all? Is that all? I'm not sure I understand that one. Can you show the male side so I'm sure I'm using the correct side? You mean of this 3-pin cable, like this stuff? So that's a male 3-pin cable and female 3-pin cable. This is what your pixels will plug into. This is what plugs into your controller using pigtails. Thank you, great presentation. Out of one power supply, what would the max injections you can typically get? There's no hard limit for that. There's just, again, going back to figuring out how many pixels you have for everything, and if that overloads the power supply or not. Can you show the solder shrink tube again when you connected multiple strings, how you do split and ground in a single wire? Sure.
So if I can say something real quick while you're digging for that, the best way to do power supplies is to come up with an Excel spreadsheet, and then you can plug in, all that data, and you can figure out how much it can use for that.
It's a good point. I think the grid is probably the better picture of this. I think this is what you're talking about. How did you split positive and ground, or it was a single wire? It was a single wire. So look at the picture on the left. That's one single wire where I've just trimmed back the insulation. And then I put all the shrink tubes down that wire I'd need. And then I cut the pixel wire and shoved it in both sides of the shrink tube and shrank the whole thing down. Fuse selection based on wire size. A 14 gauge pi wire runs into a 20 gauge pixel wire. You do it for the smallest wire. I guess I wasn't clear on that. It's always about the smallest gauge of wire after the fuse, not necessarily the first gauge of wire, but whatever the smallest gauge of wire is. You're correct. Thanks for pointing that out. I have, not only will this presentation be recorded, but I have posted those slides a couple times in the group. I will talk to Ed to see if they're doing a mailing list for them as well. And this is called Prezi. If you want to say death to PowerPoint, Google Prezi. The only thing about Prezi is it's online based, so you have to pay money to get the offline version, or you have to make sure you have a good internet connection to actually load your presentation. Yeah, the Wired Watts Learn Regulators page is a great page. I think I actually helped create some of the wording for that, or at least he asked me to. I don't know if I ever answered him. How would you wire the PS power supply on a megatree with power supply control at the bottom and one power supply at the top, with 105 volt strands? Well, that goes back to this picture. Let me find it. Let's go to the rules. Oh, I didn't want to go there. So to answer your question, visualize this string, the legs of your megatree, and one of the power supplies is at the top, one of them is at the bottom. This is how you'd wire it. You just have to make sure you cut that positive wire. Now, I actually built a second megatree last year. It was a 75 by 16, and I still used 5 volts because I really stretched that 50 rule out, and I didn't inject at the top. I only injected at the beginning of the string, at the end of the string, and then I folded over each leg. What I actually did is I created a wiring harness that was multiple connectors of these types, so that way it power injected every string based on one power injection run. So I have a giant 75 by 16 tree that runs off one 5 volt supply, and it can still power other things. So I think it also powers a couple of presents I put at the bottom of the tree as well. And I have room to grow because I used 5 volts. I just print C9 covers. Yeah, but those clear faceted ones, they're just so pretty. And nothing I can print is that clear. But yes, I don't know if anyone saw it, but last year I released those GECE adapter plates that allow you to use regular pixels with the GECE giant lenses for your lawn stakes. And that was because I was tired of the limitations of GECE and how dull they were. But I really like those lenses that come with the GECE bulbs. You needed to add a second circuit. How many pixels do you have? Is it over? I mean, what voltage are you at? Because again, 12 volt draws more, so you can usually do 10 to 12,000 5-volt pixels off a circuit. But if you're 10 to 12,000 12-volt pixels, you probably would need the second circuit. Yes. And your fogger trips your circuit breaker. Yes, my foggers do too, which is why I do have a second plug just for my foggers for Halloween. I don't use foggers for Christmas though. I don't mean have a dedicated circuit breaker, so it would have to share with other devices, lamps, computers, still no concerns. As long as your house was wired right, the whole point of the circuit breaker is if you overload your circuit, the breaker trips. So if your breaker isn't tripping, you shouldn't have a concern. Remember 0.0055 per pixel, so the math will do it. I agree. A pixel at full brightness is 0.055 amps. So that's the amps you want to use in any power equation you have. Nope, not recorded. I guess this wasn't recorded. No, it says recorded.
It's in YouTube. Everything's going on YouTube Live.
Okay.
So
Bill,
even if so, I'll make sure. Oh, go ahead.
Based on your example there, I'm about to do a mega tree with 32 strands at 100 pixels per strand. But I'm taking 8 ports off of my F16 V3 and then was going to put a separate power supplies at the base of the tree for power injection. Based on what you're saying there, initially I was planning to take both power and data from the F16 V3 and then do power injections at 8 points, as well as have 8 cables coming from the F16 V3. But seeing that you're talking about running the current in both directions, would it just be safer then just to take the data alone off of the F16 V3?
No, that violates the first pixel rule. Remember, you must always inject at the first pixel where the data is entering the string.
Right. So then could I just use then the power supply, the 4 power supplies, and just inject power at the beginning and just use those power supplies right around instead of taking from the F16 V3 as well as the separate power supplies?
It comes down to, do we go too crazy on these questions where it's just easier just to run the 3-core cable anyway, and which gives power through the pixel controller like you talked about? That's what I do. All my controllers still give power through the pixel ports like that, because since you have to not violate that first pixel pool anyway, it's just easier to wire that. Now 100 pixel legs, that's kind of in the territory where I probably would use 12 volts myself, just because you wouldn't need to inject at the top, because you could do 100 up and 100 down and inject at the bottoms instead.
Yeah.
But if there's other reasons why you're avoiding 12 volts for that, you could do it. It's just that particular case, you're looking at a little bit more complex wiring because you're using 5 volts. Like you said, you got to run power to the top.
all right, we want to go ahead and close it. Bill, thank you very much. That was awesome presentation. I'm going to go ahead and stop the live. And of course, I need to take host back first.
Yes, there's a Keith poster behind me, and that's my prize.